cos PL over 2. And then the whole term is equal to, so this is equal to, so we know that 1 minus cos PL is 2 sine squared PL over 2. So we have 2e sine squared PL over 2. Okay, so this is what we have. So from here we can determine what is our A, right? So this will be equal to 2a cos PL over 2, right? And this will be equal to 2e sine PL over 2, right? So therefore, A will be equal to sine, will be equal E sine PL over 2 divided by cos PL over 2. So this ultimately will become E tangent PL, small PL, I do beg your pardon, small PL over 2. So that is our constant A, all right? So therefore, our unique solution okay, now we are doing our unique solution. So our unique solution will become y as a function of x, and this is equal to E tangent PL over 2, and then will be, I think it's sine first. Yep, sine PX. And then we have a plus E cos PX, and then we have a minus E. Okay, so just to tidy things up, E tangent EL over 2 sine PX plus by cos PX minus by 1. This is our equation number 9. So we also do know that Y max will occur when X is equal to L over 2. And we have seen this, okay? We have seen this on the previous page, that Y max, right, over here, occur at X is equal to L over 2. So when that's the case, right, we will derive, so therefore, equation number 9, right, will become, so now is Y max is equal to E tangent PL, small PL over 2. And then we have sine PL over 2, because X is equal to L over 2, plus by cos PL over 2 minus by 1. Okay. So if we were to rearrange this a bit, so we will have E sine PL over 2 divided by cos PL over 2 sine PL over 2 plus by cos PL over 2 minus by 1, right? So we realize that when we do this, this will be equal to E, right? I'm going to make a common denominator. Okay, so the common denominator is cos PL, small PL over 2, right? So this will be equal to sine squared PL over 2 plus by cos squared PL over 2. All right, and then you have the -1 on the outside. So over here, I do apologize, it's cos PL over 2. Okay, so we know that now this is equal to we know that note, just to remind of us, sine squared theta plus by cos squared theta is equal to 1. So therefore, we have E. So this will be 1 over cos PL over 2. And then the whole thing will be -1. Okay. And then if I were to rewrite this, this will be, or if I'm going to rewrite this, Y max will be equal to E. So 1 over cosine is secant PL over 2, and then -1. Okay, and this is our equation 9a, right? So as we know, we know that small p squared is equal to big P over EI. Big P, the capital P is the axial load. So P on its own will be equal to square root big P over EI. Okay, so therefore, we will have Y max will be equal to E secant, right? And then we will have a bracket square root P big P over EI, and then we will have L over 2 and the whole thing -1, and this is our equation 9b. So that is the maximum deflection due to buckling. Okay, and this will occur at L over 2. Okay, so the next thing that we have to take note is that Y max will tend to infinity. Okay, when what? When we have the function, or we have the expression P over EI L over 2, which is equal to pi over 2. All right, when it's so 1 over cosine is equal to or 1 over cosine pi, oh sorry, what am I talking about? Sine or cosine 90 is equal to 0, right? So we know that if I were to rewrite this, right, this can be also written as what? 1 over cosine, right, square root P over EI L over 2, right, and the whole thing -1. Okay, and we know if the denominator term is equal to 0, Y max will tend towards what? Infinity, right? So for that to happen, right, square root of P over EI multiply L over 2 must be equal to pi over 2, right? So when this is equal to pi over 2, right, or if I were to write down cos pi over 2, so if pi over 2, if you press your calculator, cos 90 is going to be 0. 1 divided by 0 is infinity. Okay, so we have this expression now. Okay, so from here we can rewrite this equation over here, and now I change the P to P critical. Why P critical? Because it's going towards infinity. Okay, over EI. So this will be equal to pi over L. Okay, so the critical load is equal to pi squared over L squared multiplied by EI. Or we can write down as EI is equal to P critical L squared over pi squared. And this is our equation number 10. Okay. So we are going to substitute equation number 10 into 9b. Okay, into 9b. All right. So we are going to substitute EI equal to P critical L squared. So this is how it looks. So therefore, Y max will be equal to E, right? Secant square bracket square root, okay, P, right? EI is P critical L squared pi squared, right? Yeah, pi squared, and then we have L over 2. We have L over 2, and then we close the bracket, and then we have a -1. Okay. So tidy things up. The L can be cancelled, right? So if I were, okay, so I'm not going to skip steps. I'm going to write this out. So secant, okay, so you have square root P over P critical. And now this is equal to pi L2 minus 1. Okay, so you can cancel this. So your expression will be E secant pi over 2 square root of P critical, okay, minus 1. Yep. So let's consider the loading situation, okay, of our structure now. Okay, it's not so straightforward like eccentric loading. So for eccentric loading, we know that the maximum stress is equal to P over A plus by maximum moment over I multiplied by C. Okay, where C is the furthest distance from the centroid. Okay, so to determine Y max, moment max, so moment max is equal to P multiplied by Y max plus by PE. Okay, so Y max is the maximum deflection, which we can get from here, right? So over here, you have P multiplied by Y max plus by E. Okay, if I tidy things up. Okay. So therefore, stress max is equal to P over A, right? Plus by P Y max plus E. Okay. Then we are going to multiply by C, and then we are going to divide the whole thing by I. Okay. So I can take out P over A from I can take out P over A from here. So P over A is equal to 1, right? Plus by I've taken out P already. So this A over I, right? Then multiply by C, and then we have our Y max plus by E. Okay. So from here, we know note, right? Like what we have spoken before, where I is equal to AR squared. And R squared is our radius of gyration. So the above expression, P over A, can now be written as 1 plus by A over I can be equal to C over R squared, right? And then we include our Y max plus E over here. Okay. Then we substitute everything in. So P over A, 1 plus by C over R squared. Our Y max is this entire expression over there. Okay. Our Y max is equal to, I'm going to put a big bracket. Our Y max is equal to E secant pi over 2 square root P over critical load, close bracket, minus 1 or minus E. Okay. And then I'm going to have a plus E again. Okay. So I'm going to close bracket. And this can be cancelled. So our final form of stress max for eccentric loading is equal to P over A, right? 1 plus by EC over R squared multiply again by secant pi over 2 square root P over PCR. Okay, and this I close bracket. This is our equation. So this is the load for the maximum stress, okay, of the structure under eccentric loading, and over here is the expression of maximum deflection due to eccentric buckling. Okay, so I'm going to stop over here. Next week when I come back, we're going to do examples of eccentric buckling. Thank you.